Good morning, good afternoon, everyone. Thanks for attending this webinar. This is one of the series of webinars organized by the Computational Social Science Laboratory, Faculty of Social Science, the Chinese University of Hong Kong. I'm Bo Huang, a co-director of this laboratory. I'm very glad to chair this webinar. And today we have the distinct pleasure to have Dr. Laura Alessandretti here. She will talk about the modeling of individual mobility behavior. And before the talk, let me introduce her to you. Laura is a physicist by training. She received her master's degree in physics of complex systems at École Normale Supérieure de Lyon, and her PhD in mathematics from University of London City. Her research interests center around the computational social science, data science, and complex networks. Specifically, her research is concerned with aspects of human behavior, combining analysis of large-scale datasets, analytical models, and numerical simulations. She is currently an assistant professor in the Department of Applied Mathematics and Computer Science at the Technical University of Denmark. And she has done a lot of interesting and innovative work, published several papers in top journals such as Nature and Nature Human Behavior, which are so fantastic. So without further ado, please join me to welcome Laura. So Laura, the floor is yours.
Hello, everyone. Thank you so much for the very kind invitation. It is a pleasure to be here and present my work today. So yeah, I will talk about my work on modeling individual mobility behavior today. I will kind of guide you through a journey of like different aspects that I've been working on in the last few years. Let me first get started on what are some of the reasons why we need very rich and deep understanding of human mobility. I'll try to convince you that that's the case. One reason clearly is because we want to design efficient, sustainable, and human-centric transportation. And transportation today accounts for a very large fraction of global carbon dioxide emissions. So we want to be good at designing transport that satisfies people's needs. Out of this, like 25%, about 45% comes from road passenger transport. So like cars, buses, motorcycles. So clearly, when we study human mobility, what back in the days we used to look at was data like this. So here you can see a map of Denmark, and each sort of commune in Denmark is a node in a network. And then we have links that connect these communes that correspond to the number of passengers that we have from one place to the other. This is like an aggregated kind of like coarse-grained description of mobility. But in fact, at the end of the day, this sometimes does not capture what is actually individual choices. So here is people traveling from one place to the other, but people can travel in many different ways. So this is, for example, like rush hours in my hometown in Italy, Turin. Lots of people driving around in the cars being stuck in traffic. This is actually rush hours in Denmark, where everyone goes around cycling, or not everyone, but lots of people cycle around. So this is very different type of mobility. And we need sort of like a deep understanding to realize what are the factors that determine why people choose one mean of transportation versus another. One may think maybe it's weather, but in fact, people in Denmark cycles with all types of weather. And when I mean all type of weather, it's like all type of weather. And we want to kind of like capture these differences, these heterogeneities, and what are the factors driving spatial choices and mobility choices in people. Another important societal challenge that we face today is clearly understanding the spread of epidemics. And importantly, the spread of epidemics is deeply intertwined with human mobility behavior. So here you can see some snapshots taken from a website that we've been developing with my team at DTU. Together with them, we basically monitored what was happening in Denmark throughout the pandemic and how mobility patterns have changed over time. But here again, often we have a coarse description of what's going on, and often this is not sufficient. In fact, what we discovered is that when we studied mobility changes over time throughout the pandemic in Denmark, we were seeing that people drastically changed their mobility behavior in time. So here you can see a curve describing the total number of trips performed in Denmark all throughout 2020. And we clearly see that there's some different phases that often correspond to the introduction and removal of non-pharmaceutical interventions. And something we discovered as we were studying this phenomenon is that, in fact, this curve tells only like a part of the story. This curve is, in fact, a superposition of different types of mobility behavior. One that captures commuting, so that captures people daily trips and going to work. One that captures leisure trips, so what people do like during weekends when they travel for leisure, and one capturing vacation. So this kind of like combined aggregated mobility metrics do not really describe the entire situation. And we need sort of like better tools to capture all these different types of mobility and understand how they have changed and how these different types of mobility contribute to the spread of epidemics. So we want like a richer understanding. This study sort of like showed that we can extract these patterns from aggregated mobility data. Was published in the Philosophical Transactions of the Royal Society last year. And you can find more about what I mean there. So again, here what I want to sort of point out is that we don't have a complete picture when we study like aggregated mobility patterns, and sometimes we really need to narrow down to study the individual level. So when it comes to, for example, studying the spread of diseases, what is clear is that human mobility is necessary to the spread of infectious diseases. Why? Because for a contagious event to happen, we need two people to meet. So we need people to travel to meet each other. So this is kind of like a necessary condition that if a contact has occurred between two people, clearly these two people had to move to come in contact with each other. At the same time, the human mobility is necessary, but it's not sufficient, because it could be that one traveled for other purposes. So it traveled for going for a run, for example, for jogging. So counting simply like the number of trips that people make over time is not enough to sort of capture contacts and the spread of diseases. And often we need to go one step further. This is also like a commentary that I wrote sort of based on what we've learned during the pandemic on the spread of infectious diseases and interplay with human mobility. It was published in Nature Reviews Physics. So here, basically all this is to say that we kind of wanted to move away from this like coarse description of mobility, and we want to narrow down to the individual level and understand how single individuals take spatial decisions. And this is often necessary to capture these like subtle differences between different types of mobility and different purposes for which people move. And in turn, understanding these aspects is really important to tackle the societal challenges that are really deeply intertwined with mobility behavior. And this is basically where my work has been focusing on understanding how people take mobility decisions. Let me guide you a little bit through my journey in understanding individual behavior. First of all, this opportunity to study mobility behavior at such high resolution is made possible by the availability of data collected from phones. Back in the days, it was not possible. And now, because most of us walk around carrying a phone, then we can actually understand mobility behavior at high resolution. So here I'm briefly describing two of the data sets that I've been using for my studies and that capture mobility behavior of lots of individuals worldwide from GPS traces collected from phone. So one is a data set of about like 1 million users collected between 2015 and 2019 all around the world. And we also have some metadata about individuals. The second data set was collected at DTU, which is the university where I work, between 2013 and 2015. And we also here have a very high spatial and temporal resolution because, again, we're looking at GPS data, which is really high resolution. So the first thing is like, how do we model mobility trajectory of an individual? In the simplest form, a mobility trajectory is nothing but a sequence of places. And so you can see here just like a sequence of different places. And this is sort of like one of the first things that people have looked at is like, how do people visit different places in sequence? And one can understand these sequences as a chain of what we call exploration and exploitations. Because the idea is that at any point in time, say when we want to go to a bar or to a restaurant, we can choose whether we want to explore a new restaurant or a new bar, or we want to go back to a restaurant we've known before. And this is sort of like a classic dilemma in understanding behavior, is whether people prefer to take a risk and go and explore a place, or rather exploit something they've seen before. So one of the first things that we found out, or that researchers have found out looking at GPS traces collected from phones, is that in fact, while we visit like lots of different places, it turns out that when we look at like how many places people visit very frequently and they go back to very frequently, this number boils down to a very small number of what we call familiar locations. So you can think of those as home, work, maybe like a favorite bar, favorite restaurant, friend's place, and so on. And it turns out this is a very small number of places. We call it an activity space of frequently visited locations. So when we look at like how much time people spend in this like activity space, it's really like a large fraction. So you can see here, this is a curve extracted from one of our data sets, and people spend in about like 12 locations, about 95% of their time. So it's really like a large fraction of time in a small fraction of places. At the same time, something that had come up in the literature is that when we look at the exploration rate, so how much people explore new rate, we find that people keep exploring. So despite the fact we have a small set of familiar favorite locations, we still keep exploring more and more places. So this curve describes the number of locations discovered over time. And we can see that this has a sublinear growth with exponent 0.7. So people keep exploring places in time. And so one of the first questions we asked ourselves is like, how is that possible that we maintain this like stable set of places and at the same time we keep exploring? What is the interplay between like exploration and exploitation of places? And the approach we took to kind of like study this interplay is by considering like a sliding window of several weeks to kind of like understand how the activity space evolve over time. So we look at the locations that are included in the activity space within the sliding window. And what we find is that in fact, this activity space of locations evolve in time. So we don't keep the same familiar locations over and over again. What you see here in the figure is the Jacquard similarity between the activity space at any given time, and then 10 weeks later, 20 weeks later, 30 weeks later, and so on. So basically, after about a year, the activity space of familiar location looks very different than how it looks previously. And this is something that we have observed for different data sets with very different natures. So it doesn't necessarily have to do with certain specific subset of users being different than others. It's really the way it is across data sets. So our familiar places change. At the same time, we found something extremely interesting, which is that despite the fact that this activity space of places change, their number remain constant. So we still keep the same number of places familiar all like over time, right? And so we suggest that there is some kind of spatial capacity. So we have a maximum capacity of like number of places that we can accommodate in our daily life. And here again, this result was confirmed across datasets, and the spatial capacity varies. Some people have larger capacity, some people have smaller capacity, but the idea is that this number is conserved at the level of the individual over years. So another way to see this is to basically say that whenever we introduce a new place in our set of familiar locations, it could be like a new restaurant that we like to go to, there must be a place that is kicked out from our set of familiar places. That could be, for example, like an old restaurant we don't go to anymore. All right, so how can we model this idea of exploration and exploitation? There is a widely used model in the literature that's called the exploration and preferential return model, that suggests that anytime we want to go somewhere, we can either explore new places with a given probability, and this probability depends on the number S of locations that we already know, or we can exploit a place that we already know with a complementary probability. And when we exploit a place that we already know, we will basically pick in a preferential return fashion. So places that have been visited more will be visited more and more. So the idea is that the probability of visiting a given place is sort of proportional to the number of times we have already visited this place in the past. What we found out is, this was the state-of-the-art model at the time. What we found out in this work is that the preferential return model is not able to explain this evolution of familiar locations over time. So we introduced an idea of memory. So we added a memory, and the idea is that we only remember locations that we have seen in the last few months or so. And by adding this simple like memory effect, we figured that our model was much better at reproducing the observed properties. So what you see here in the top is the capacity, the spatial capacity that is well reproduced both by the exploration and preferential return model and by the exploration and preferential return model with memory. What you see in the bottom figure is the evolution of familiar locations. And as you can see, the exploration and preferential return model without memory does not allow for these places to change over time, to evolve over time. So memory is kind of like a key effect in human mobility, or some kind of like recency, you can also call it. All right, so when it comes to sort of modeling places or visits as sequences of locations, we found out that individuals allocate time within an activity space of few locations. And this activity space changes gradually over time, but it has a constant size, so a constant number of locations that are visited regularly. And when we have an exploration exploitation model with memory constraints, we're able to reproduce the observed properties of human mobility behavior. But the thing is that if you think about it, this is only part of the story, right? So mobility trajectories are not simply like sequences of places. There are elements that we have kind of like not pay attention to so far. So you can think of mobility trajectory actually as sequences of places that are embedded in space. And this adds a layer of complexity to the problem, because we want to understand what is the role played by distance between different places and how that affect our exploration, exploitation patterns, and in general, like spatial behavior. So when we started tackling this problem, we sort of like relied on what was the known literature at the time, and what had been found about the role of space by the literature was that, in fact, human mobility is what they say like scale free, so that there are not typical scales in human mobility behavior. Here in this slide, I'm reporting some titles of different studies that were published in different like important journals before sort of like our work that I'm going to talk about right now. And you can see that in many of these titles, you see appearing the word scaling laws, scaling properties, scaling identities. And these basically are all synonyms for the fact that we have no typical scale was found in mobility behavior. And let me dig a little bit more into what this means exactly. When we study a mobility trajectory, we can see it as, again, a sequence of displacements, right? This is what we've seen before. So we have a sequence of places, and we have basically the displacement between one place and the next. And each of these displacements is characterized by a length. So it's kind of like the distance we travel to get from one place to another. Here, what you see is an actual GPS trajectory, so the black line. And the red lines are kind of like what we extract. So the places and the displacements between one place and the next. And we extract this length or these distances that we travel. And then something that we can do is like we can plot the probability distribution of traveling at a given distance or traveling at a given distance. As this is what you see. Here, it's a figure extracted from one of the sort of first large-scale studies on human mobility, understanding individual human mobility patterns, published in 2008. And you can see that when we plot the probability distribution of displacement, we see in log-log scale, so when the x-axis and the y-axis are in logarithmic scale, we see a power law distribution appearing. So a power law distribution is a straight line in log-log scale, and in particular in the tail of the distribution, we have a power law function. So a power law function is the typical signature of scale-free distributions because it's a probability distribution that has no typical scales. So it's kind of like less and less likely to travel at a given distance, the larger the distance, but we don't have a specific distance that people prefer to travel at. So if you think about it, this is a little bit counterintuitive, because when we think about space and when we think about mobility, we really think of space in a hierarchical fashion. So if you need to kind of like grab a coffee, that's something that typically you can find within the scale of the building. So within a university, you know, you want to grab a coffee, you can find it there. If you want to go to a restaurant, that's something that you can find within the neighborhoods. If you want to, say, go to a stadium or a cinema, that's something you find in the scale of the city. If you want to go to an airport, that's something you find like in the urban agglomeration around the city. If you want to maybe go on holiday, like for a weekend off, you can go somewhere within the country, and so on. So we have really like these different scales, these different typical structures that embed our movements from the building up to the continental scale, right? So this is something that we're very familiar with, and it's actually something that has been found in spatial cognition as one of the ways that we actually capture and think of space in our brain. So we think of space in this way, in a sort of like a hierarchical fashion characterized by typical scales. So here we were a little bit puzzled by the fact that empirical findings on human mobility found no evidence for characteristic scales, but at the same time, spatial cognition suggests that we do have typical scales that characterize how we think of space, and that should affect also the way we move. So how we tackle this problem? Well, we started by designing a new model for individual mobility behavior, where we try to reproduce precisely this idea that we move in this like hierarchical structure of buildings, neighborhoods, cities, countries, and so on. And we call this the container model because each sort of building, city, region, country, it's kind of like a container for our mobility. It tends to keep us within the container, and we tend to transition across containers a little bit less often. So space is a nested structure of compact containers with similar sizes. And you can see here on the right a sort of schematic representation of this spatial container structure. So we have locations that are black dots that are embedded in neighborhoods, that are blue circles, that are embedded in cities, that are orange circles. And you can sort of like go on and imagine this like hierarchical structure. And then the second assumption of this model is that this structure shapes the way we move. So we move across, in this a hierarchical structure, and we're shaped by the way the structure functions. So the hierarchical container model has three elements. So one is this sort of like hierarchical partitioning of space. And then we have what we call the attraction of each container, because, for example, like the place where we live, so our home container is much more attractive to us than someone else's home. And then we have the probability of traveling across levels. So it is clearly much more likely to travel in the same building than to travel across countries. So these are the three elements in this container model. And once we have these three elements, we can basically generate synthetic trajectories. So we can imagine an individual, and this is basically an agent-based model that we can use to just generate some synthetic trajectories. And we have a sort of equation that describes what is the probability for an individual that is located in a given place L to travel to any other place K. So we have a probability of going from L to K that can be simply expressed once we have all the elements set up. So once we have the hierarchical structure, the parameters, and the attractiveness. So once we have this generative model, this is a generative agent-based model, we can just generate traces. And here what I'm showing to you is a synthetic trace that we generate with our model. It's on the left, and on the right, we see the probability distribution of displacements. So what we have seen before, and you can see that it has some bumps, but it also has this kind of like power law shape. And you can see the synthetic trace on the left, it's colored. So we have certain displacements that are red, certain displacements that are green, because we have precisely that we have movements across different containers. So we have movements within buildings, movements within countries, movements within regions, and so on. And so the idea is, okay, what if we have this like synthetic trace, but we don't know the colors? So we don't know what is the hierarchical structure underlying this trace, and we don't know the colors of this trace. So we have a gray trace. Can we reconstruct this like hierarchical structure that generated the trace? And the answer is actually yes. So why? Because we can use maximum likelihood. So we have an agent-based model that has a specific sort of probability of transitioning between any pairs of places. So once we have a trajectory, so it's a sequence of places, we can simply compute for a given candidate model what is the probability that this candidate model has generated that trace. We can simply write that down, and we can write the likelihood of the trace given that specific version of the model with that set of parameters. So here you can clearly see that if we can do that, we can basically compare many different models with many different combinations of H, A, and P, and find out which model is the most likely to have generated a specific synthetic trajectory. So this is what we actually did, and we found out we were very good at that. So we could basically just reconstruct the underlying model for a given trajectory. And I guess you're also seeing where I am going, that once we basically have a way to reconstruct the hierarchical structure underlying synthetic traces, we can do exactly the same thing with real world data. And this is what we did. So now what we see on the left is an actual trace of an individual that has consented to share this figure. What you have on the right is the probability distribution of distances, and we can just color the trace. So we can just find basically for every single displacement, whether it occurred within a building, within a neighborhood, within a country, but it's not the sort of administrative definition, or it's not something we take from external data, it's just something we infer from the data. Now, this basically means that we can also, let me see if I can do this. Okay, yeah. This basically means that we can also extract for each individual the precise containers that describe mobility behavior. So here is an actual individual and who lives in Copenhagen. And what we can find with our method is what are the neighborhoods, so the blue containers, the city, so the orange container, the urban agglomeration, so the green containers, the regions, so the red containers, and up to the continent, which is this like purple container. This is something that we can extract for every single individual in our dataset. So each of us has their own different hierarchical organization of mobility. This is purely extracted from mobility trajectories. And I mean, if you have ever been to Copenhagen, this is something that makes a lot of sense. This kind of like matches pretty well with the administrative organization of the city around Copenhagen. And now imagine that you can do precisely this thing. So this sort of like extraction of like hierarchical structure for every single person in our 1 million dataset that is collected worldwide. This is what we did. So we did precisely this thing for everyone. And, oops. All right. And what did we find? So the first thing we found is that people have multiple scales. So this is the number of like hierarchical levels that people have. This is the distribution. And we find that on average, people have like 4 hierarchical levels in their structure. And this was not given. So we could have found maybe that there were no levels, and this would have basically told us that trajectories are scale-free. But no, trajectories are not scale-free. We do have typical containers with specific sizes. And when we look at precisely the sizes of these containers, we find that when we look at the distribution of sizes of containers over individuals, they do have a typical size. So the first container has typically a size of 3 kilometers, and people spend on average half a day within a container before transitioning to another level. And we basically have that the second level has a typical size of 30 kilometers and so on. So we have actual characteristic typical sizes across individuals in this like large scale data sets. So there are typical scales in human mobility. Now, what can we do once we have this model that gives us like a better understanding of individual mobility behavior? Something that we can do is to generate more realistic synthetic trajectories that we can use for exploring scenarios in a new city where we don't have data for example. So what we did with this data set is that we trained the model, so the container model, using 1 year of data, and we generated new synthetic movements for each individual. And then we compare the properties of synthetic trajectories, synthetic movements to unseen data to find out how similar they are. So one of the things that we looked at is the so-called radius of gyration. So the radius of gyration is basically a typical radius that describes the extent of an individual movement. So here you see a map of Denmark again. You see red dots are individual locations. And we can basically study what is the characteristic distance traveled by an individual. This is a very typical metric that is used in human mobility to quantify the extent of individuals' whereabouts. And it should capture how far people travel on average, basically. It's really like a standard metric in human mobility. And when we look at this metric as a function of time, this is the data, so the black dots. This is the container model, so the orange line. This is the EPR model. So it is one of the standard models in human mobility, as we have seen before. So what we can see is precisely that the container model captures much better the actual evolution of the radius of gyration compared to the EPR model. So we are much better at sort of like predicting future movements and generating traces that are realistic. All right, so when we think of like what I wanted to sort of like convey with this study is that human mobility is characterized by spatial scales, and we now have a method to unveil these spatial scales using our container model. And the container model helps us understand human movements and generate realistic synthetic trajectories without overfitting. So we generate trajectories that are much more realistic than previous models. This is the study that was included in a paper called The Scales of Human Mobility, published in Nature. Now, something else that I've worked on after the study was published was sort of to kind of like extend this metric, the radius of gyration, that is used in the human mobility literature to characterize the extent of someone's whereabouts. So if you have human mobility that has some kind of like monocentric structure, so where we sort of locations are clustered around a given center, like in this schematic description, the radius of gyration captures really well the extent of whereabouts, right? So you have a cluster, you have a center of mass, so the star, you have a radius of gyration that sort of capture this circle, this red circle that captures most of locations. And here is where we want to use the radius of gyration. But when instead you have a polycentric structure, so people visit sort of different containers, right? Like we've seen in real world data. And you have sort of like multiple clusters of locations, like you see in the schematic description on the right, then the radius of gyration may not capture so well what we want to what we actually want to see, right? Because here we have multiple characteristic distances. As we've seen in the scales paper, we have lots of different typical distances and not just one. So the radius of gyration is not enough to capture polycentric distributions of locations. So in this paper that is now an archive preprint from Center to Centers, Polycentric Structure in Individual Mobility, we propose an extension of the radius of gyration, where we precisely propose to sort of look at different centers and different radii that capture the distributions of locations that are polycentric in nature. So where we have multiple clusters of places that we visit. In individual mobility, we show that mobility is polycentric, and so it's better captured by multiple radii of gyration. And this is like an archive paper and a work in progress paper with Renaud Lambiotte and Rohit Sacharabuddhe. All right, but so we've seen that basically we're kind of like adding elements one after the other. So the first element was locations as so mobility as a sequence of locations. Then we've seen that sequences of locations can be embedded in space. So that was what we've seen with the scales paper. And importantly, what I want to show now is that we have forgotten the individual so far. So we have forgotten that people are different, and we are all different because we live in different places. We have different backgrounds. We have different needs. So we now want to kind of focus on the individual in the mobility trajectory. And I want to see what we have done so far to sort of characterize how different individuals have different behaviors simply because they have different needs. So one of the things that we found out when we look at the results coming out from our containers model is that the size of these containers are different across individuals, right? And one thing that we looked at is like how different they are for females in comparison to males. And what we showed is that in general, females travel less. So these mobility containers are smaller for females, as if they were to travel shorter distances in general. So here what you see is the size of containers across different levels for females and males. And you see that for females, containers are on average smaller. However, something interesting, and it was a bit unexpected, is that despite the size of containers being smaller for females, we found that the number of levels, so how many levels we have in this like hierarchical structure describing human mobility, are more for females. So the number of levels tend to be larger for females, so the red line, compared to males, which is the blue line. In a way, this was a bit unexpected because it is well known that females move less, but here what we show is that females have a more complex mobility behavior in a sense. And when we look at like how this changes across countries, we see that this gender gap, so this difference between females and males, is more pronounced in certain countries that are here on the left. So these are countries where this difference is more pronounced and is less pronounced in other countries, so that are here on the right. And when we plot the gender gap in number of scales against the gender inequality index that captures like how much inequality there is across gender in a given country, and it's measured, start looking at like differences in representation in the parliament and employment gap and so on, we see a strong correlation. So we see that basically the gender gap in mobility that we can capture with the container model reflects quite well the gender gap in mobility that we have in a given country. So here each dot is a country, right? This was very encouraging, first of all, because it means that with a container model, we can capture actual differences between individuals, and we can capture something important of mobility. And also, again, was a finding per se, because we clearly see that there is a gender gap in mobility in some countries. So this is something that I'm working more on, this idea, differences between males and females in the number of scales, and also in general in mobility. And something we've been looking at is differences across genders in the mobility entropy. So the mobility entropy, like the equation is here, is basically a measure that for a given sequence of places captures how regular is this sequence. So here P of K is the probability of visiting a certain location K. So the idea is that the larger the entropy and the more diverse is the set of places that are visited by an individual. And what we've tried to do here is to kind of like predict this mobility entropy for different individuals based on different characteristics of the individuals. And there are different things that we can measure in our datasets, including like age, urbanization, gender, country of residence, and employment status. So here we tried, first of all, by running like a simple like regression model, starting from like all these different factors. And what we found is that we can explain about like 14% of the variation with a simple regression in entropy, with a simple like regression model, by looking at like all these different factors. And interestingly, while gender does explain part of the variation, the effect of like employment status is much larger, right? So to an extent, these differences that we observe in mobility behavior across genders seem to be driven by a difference in employment status. So the fact that women are more likely to not to be employed. And we actually try to run like more complex models. So here is like a gradient boosting models. And we show that we can, by looking at sort of like more complex models, we can achieve like a higher R squared. So we can achieve a better description of the data, and we can go basically up to like 16%. So we can explain up to like 16% of the variation in the data by looking at these different quantities. And here is like a more sort of like in-depth exploration of the results. So here we actually looked at only like 2 countries. We look at like Spain and UK, and this is a work in progress paper with Silvia de Sojo Caso and Sune Lemon, where we try to kind of like dig into these differences across genders. And you can see this is the this is basically a figure showing how different variables contribute to the outcome of the model. And we can see that, for example, when it comes to the employment status, so people that are employed, so this like red cluster, this contributes negatively to the entropy. And for people that are employed, so this unemployed, so this blue cluster, this contributes positively to the entropy. And for gender, we have that for females, so these like red cluster, we have actually a larger entropy than for males that are this blue cluster. And age also has an impact, because people that are younger have larger entropy than people that are older. And urbanization has an effect, because people that live in like highly urbanized in highly urbanized areas tend to have higher entropy than people that live in rural areas that tend to have lower entropy. So in a sense, what we show here is that there are, to an extent, some of the heterogeneities across individuals that we can explain resorting to some of these like individual differences, because we have simply like different needs. So yeah, here's what I wanted to sort of conclude by saying, that we have that some of the statistical properties of individual mobility are shared across individuals, but we still have like a large level of heterogeneity across people. And some aspects like socio-demographic and environmental aspects, such as employment, age, gender, urbanization, can explain to an extent these heterogeneities. And we found like up to 16% in our data. All right, so I'm getting to like the end of this talk. Then I hope to have some time for discussion. But so to summarize, what I wanted to share with you is that modeling individual level mobility is crucial to tackle some societal phenomena, and we need like a very rich and deep understanding of mobility behavior. So thanks to mobile phone data, we have come a long way. So we have used different approaches and show that it is possible to a large extent to understand how people visit sequences of locations and what is the role played by distance, and to an extent, what are some of the heterogeneities across individuals and what factors explain these heterogeneities. But we still have a long way to go. So there's still lots of things that that are unclear, and some of the things that I'm working on are, for example, routing, which means how do we get from one place to another? So not simply like where do we go, but also how do we get there? What transport mode we choose, and what is the effect placed by location semantics? So the fact that locations have different types, right? We can go to restaurants, we can go to schools, we can go to visit like different type of points of interest, and what is the role played in mobility by these different aspects. So these are all things that are still a little bit unclear, and I think there's a long way to go in the research. Like the research has some work to do. And yeah, another important aspect is that as data becomes richer and richer, and we have more and more elements, to include. We can combine simple approaches like the one that I showed that are based on like agent-based modeling and simulations with more complex models like deep learning approaches that enable to capture some of these like interdependencies between different variables. And yeah, I think that there are already some very promising results coming from like deep learning models for modeling individual mobility behavior. And I think that by combining the two, we can potentially like achieve more than by using one or the other. So I think that's it. I really want to thank all the collaborators that have worked with me on these different projects that I presented here today. So from Technical University of Denmark, City University, University of Oxford, at University of Northeastern, all these colleagues have worked with me on these projects. And I really want to thank you all for coming today. It's really a pleasure to be here, and I hope to get a lot of questions from the audience. I look very much forward to the discussion. Thank you so much.
Yeah, thank you, Laura, for the very interesting, very insightful talk. Also very thought-provoking. So now the floor is open. So any questions? Oh, actually, we have got a question in the chat window. So yeah. David, would you like to ask directly or? Yeah, maybe I can read the question and then it can be recorded. So I would compare your work with Jeffrey West's and propose two questions. One is, what is the driving forces within the scaling law of mobility? For West, we discussed based on the rule of energy use and other physical laws. Do you have some similar explanations?
Yeah, so one of the, so there could be like lots of different reasons that combined. So partly this could have to do with like the hierarchical structure of the transportation systems. So we move by, so we have this like different containers, right? From here we go. from the rooms to the neighborhoods, the cities, the countries, and so on. And we also use different transport modes typically to travel at different levels. So we walk, we take the train, we take the plane, we take the buses, and so on. And these have different like speeds. So to an extent, it could be that some of this like hierarchical structure is connects to the structure of the transportation system. But partly it simply has to do with the way we think of space. So this is kind of like how I started the talk, and it's because it's really been proven empirically that the way we think of space is this like in this hierarchical fashion. So the fact that we tend to have some kind of like think about when you want to go out for lunch, like you're at uni and you want to go out for lunch, you have some kind of like radius that you are willing to walk to go for lunch, but kind of like no more than that, right? So there is a limit to how far you want to travel for grabbing lunch, and that sort of corresponds to that draws like a radius around the university, and this is kind of like how far we can get to go for lunch, but no further. So this is the explanation that we have, and we haven't proven like this connection between the cognitive aspects of it and the behavioral aspects, but because it's proven that we do imagine space in this way, this could be one of the explanations for sure.
So his second question is, West finds some scaling laws related to the size of cities. Is there any scaling relations between scale of mobility trajectory and city size? For example, people travel longer distance in larger cities.
Yeah, so what we found is that partly these sizes of containers have to do with the availability of resources. So it is quite, in fact, the opposite, that in rural areas where there's less opportunities. So there's less bars, there's less restaurants, less supermarkets and so on. People need to travel a little bit further to access the same resources than in cities where there's high density of points of interest and opportunities, right? So it tends to be actually the opposite. And these sizes have partly to do with the access to resources. And the more resources you have around where you are, and the smaller these spatial containers are.
Yeah, great. So any other questions from the audience?
Hi, Professor Huang. It's Xintao.
Yeah, Xintao, please, sure.
Okay. Hi, Laura. It's Xintao from PolyU Hong Kong. Thank you very much for sharing a very interesting topic. I just have a very quick question. You used a container to divide the human mobility into different hierarchies. So I was just wondering, are there any other possible ways to divide the human mobility into similar hierarchies instead of the container model? Thank you.
Yeah, this is a very good question. We've tried hard different methods. So this is a result of a work that we've been doing for years. And so there may be other ways for clustering locations in an unsupervised fashion, but we found that none of them would work. And there's some reasons for it. So first of all, we have this interplay between space. So one could run some kind of like spatial clustering methods, but this does not capture how we actually visit locations. And on the other hand, we have a network of places that we visit one after the other. So for example, we tend to, go from home to work a lot. So home and work are two locations that are highly connected, no matter how far they are. And so we have these sort of two layers. On the one hand, we have the spatial level, and on the other hand, we have the sequence of visits. And we found out that basically like combining these two aspects with other methods was harder. So we couldn't find a way. And on the other hand, in general, the modeling approach is just better because we have an understanding of what's going on under the scene. So this is a generative model. It's a model we can use to generate traces. So it's much more principled because we have precisely some mechanisms that underlie the sequences of movements and we understand and that we can use to generate more traces. So these are two of the reasons why we think it's a modeling approach is just much better than any other like unsupervised approach that one could use to cluster locations.
Okay, thank you very much.
Okay, so we got a question in the chat window. Thank you for sharing your excellent work. Two questions here. In the work of container model, I wonder how to determine the container size and the number of levels. The second question is, are the container sizes consistent with the neighborhoods, cities, states, and nations?
Yeah, so the first question so we used maximum likelihood. So we basically have several candidates model, and we explore like in a greedy fashion the space of possible like hierarchical structure, and via maximum likelihood we found the hierarchical structure that is more likely to have generated the sequence. So this is when we stop. So basically when we add another layer but we cannot improve on the likelihood, then this means that it's not necessary to add a new hierarchical level and improve on the likelihood, right? So this is what we do to determine the number of levels. And when it comes to the size of containers, we again, like we try sort of like different configurations until we find the set of containers that maximize the likelihood. And regarding the second question, what we found is that containers are very different. So it's not like they reflect like administrative boundaries, or anything for everyone, but every single person has their own, and they're very different. So this is really to do with the way like each single person experience space, and it doesn't have to do with administrative levels so much. And we started to explore a little bit how they compare to the administrative structure, but we couldn't find really strong connections. So yeah, but it is something that we need to explore a little bit more because we haven't explored in detail. Yeah.
Sorry, I missed your answer a little bit. How to measure the container size? So in terms of the maximum distance, a traveler travel within certain level of a container.
Yeah, so the container size, it's basically, so we measure like the average distance between so between the center of the container and sort of like the border of the container, and then we take an average. But so the way they're built in is that they have approximately similar sizes. So the average distance is sort of typical across containers, right? So we have an average distance.
Okay, yeah, thank you. The next question asked by Jiarong Li. The scaling law will vary according to different travel modes or remain the same?
Yeah, this is a good question. So there is a paper by Mirko Musolesi, published some years ago, which basically shows that in fact we can basically decompose the scaling law into travel modes, and that different travel modes have sort of like different travel distance clearly, so that the power law distribution partly emerges because we combine different travel modes, and this reflects also very well what we find, that we have typical containers, and that when you combine them together, you produce the scaling law. Yeah, so we haven't really checked with our own data because it's kind of like inferring transportation mode is not like straightforward, and we don't have like labeled data where we know what transport mode people have used, and often people combine multiple transport modes for the same trip. But yeah, so the containers and the transport modes are surely related, and it is something that we need to explore further for sure, because as I was saying, people tend to like use walking for traveling at the lower levels, and we tend to use like faster transport modes for traveling at higher levels. So the two are clearly connected. And if we had labeled data, we could explore these connections.
Yeah, thank you. Then Jacoby, Richard, Thomas, please.
Yeah, hi. Thank you. It was a fascinating talk, and I'm wondering if, now that you have these containers like mapped out and like the transportation networks, if there's a way we can like enrich the story more substantively with qualitative data, because beyond just like the Euclidean physical distance, there's all this social distance that could be very different with everything. I mean, obviously there's physical things too that may matter, like elevation, but I'm thinking like crime rates, traffic, like a lot of other kind of things that hot places, that spaces that people, or places that people feel are hot or cold for whatever reasons, past experiences, people died there, all types of things depending on the history of a city, and how that physical space and that social space in terms of people's perception of what's far away or near might be different from each other by bringing in more of that like qualitative observational data.
Yeah, really cool. Absolutely. So yeah, you're right. We used Euclidean distance, and to an extent, physical distance correlates with the temporal distance, which is one of the like cost functions that are most like used in this type of like studies, because what people care the most is like how long it would take to get from one place to the other. So this is the typical like cost function for understanding like the cost of getting from one place to the other is like how long it takes to get there. So, and this is what is widely used in the literature. But at the same time, you're right that there's other type of costs that are not necessarily just time or space, but they may have to do with some kind of like cognitive distance. There is some very interesting work by Ed Manley from UCL on measuring like the cognitive distance between like two places. And that has to do with, for example, like having to cross bridges or having to go through places that have, so that two places that are close in space may seem like actually far for some kind of reasons that doesn't have to do necessarily with the physical distance or even with the time it takes to get there. So I think these would all be like awesome things to do. As I said, there's a lot to be done, and especially there's a lot to be done when it comes to precisely measuring like the path that people take to go from one place to the other. And this is because it requires very high resolution data, GPS data, and it requires kind of like infer transport mode, infer what like route people took, what were the other options available. So everything that has to do with kind of like measuring what's along the way, there's still a long way to go. But I agree, it would be extremely interesting, and I agree with you that there may be tons of reasons why people don't travel between any two places, even if they're close. And this is exactly what we see with the containers, is that two places may be very close, but for some reasons people never travel there because these containers contain their movements in a specific area. And it could also be very personal, as I say. So it could be that, and this is what it seems to be, that individuals that live close by, they have completely different containers, even though they live close by. And we should find out why and what are the reasons why.
Okay. So any more questions? Yeah, actually, I have several questions. So you have the actual mobility data. Why do you need to do simulation? So you want to prove or validate what kind of thing? Sorry, I didn't get that.
Yeah. So, I mean, we have a model that can generate synthetic traces because there are instances where we don't have data. So it's true that we do have some data, but we don't have all data. And it is an interesting question, like to what extent we can generate synthetic traces in areas where we don't have data, for example. So this is also something that I'm working a little bit on right now. So we're trying to see how much biases we have in mobile phone data and whether we can use this data to generate synthetic traces in places where we don't have data, or for people that are not in our sample, to what extent we can transfer, because there are people that own a smartphone and that are in our data sets that come from some specific set of smartphone users have some biases. So it's not for granted that we can necessarily like use this data or use these models to generate synthetic traces in places where we don't have data. But the answer is that, yeah, we don't have data everywhere and for everyone on Earth and for all time periods. So we may be interested in seeing like in generating data in situations where we don't have it. So that's why. And it's not granted that it will always work out, precisely because there's biases in mobility data. So
yeah, great. So I understand the mobility within one scale. For example, within a city, the distance follows the log normal distribution. So if the mobility contains two scales, then it follows the power law distribution. So do you mean if it includes more than 2, then just follow the power law, it's scale free. But if it, I mean, I don't quite answer this. Yeah.
Thanks for the question. It's really important. There's something I skipped a little bit in the slides, but the idea is that, so one of the way that one can generate a power law is by superposing distributions that have a specific scale, but different variances. So this is one of the way one can generate a power law, is by superposing distributions with a typical scale. So the idea here is that when people have several scales, then the combination of these distributions generates a power law.
Okay.
Does this answer?
Yeah. Okay. So any question from the audience? So if no question, here. We got another questions from Xinye. So thanks so much for sharing your wonderful work. Container model is a very interesting and effective model to simulate and generate human trajectories. I just wonder how to define different hierarchical levels or the total number of hierarchical levels. If we use different spatial scales to define containers and hierarchical levels, such as within a city scale or country scale, do the sizes of containers and hierarchical levels change?
Yeah, so okay. So if I understand correctly, you wonder like if I don't have like data for like across all distances, but we have only a portion of the data, how that impact the results of the model. So we haven't tried, to be honest, but my sense is that if we remove sort of like long distance travel, for example, this is a realistic scenario where we don't have data across all countries, but we only have data, say, within a country, then we would only find the low hierarchical levels. So we would find like the building scale and the neighborhood scale and the city scale. So surely the data resolution and the coverage are very high when you look at GPS data. So we have very good resolution. We can go down to the building-ish scale and across continent scales, but not all data sources have this level of resolution and coverage. So if we don't have such resolution and coverage, then we would basically just cover like a narrower set of scales. Yeah, that's a good point.
Okay, Xinye, do you have more questions? Yeah, okay, actually, I have another question. So if I understand correctly, we can use the previous gravity model to estimate the trip distribution. And now you propose the container model, which is better than the EPR model because it accounts for the several containers involved in the trips. Is that right?
Yes, so good point. So the thing is that the EPR model somehow doesn't focus as too much on the effect of distance. So in the EPR model, the power law distribution of displacement is kind of like an ingredient of the model. And it's kind of like, this is the way it is. So when people like travel to a new place, we assume they extract a distance from a power law distribution and they just travel at that distance. But they don't really try to find like an explanation for why we extract a distance from a power law distribution. So why would that be? This is kind of because the focus of the EPR model, it's really to model the trade-off between exploration and exploitation, and they just take for granted that we have a power law distribution of distance. but it doesn't focus precisely on why is there a power law distribution of distances. And here is just like the idea with the container model is that it complements the EPR model. It's not an alternative in effectively, because it focuses on another aspect, which is not the interplay between explore and exploit, but it's where does this power law distribution comes from? It comes from the superposition of scales. This is the answer of the container model. So the two models in a sense are complementary and they focus on different aspects.
Okay, so to jump in, if it involves more than one container, then it becomes kind of difficult to travel. For example, if I go to Beijing, I mean, because two systems are involved, then I mean, I need to go through the customer, etc. Then it seems that it becomes more difficult than the direct trip from one place to another place.
Precisely. So yeah, the idea is that traveling far it's less likely. So just like it is in the so yeah. What I was saying is that it's precisely the case that when you travel to another country, there's some kind of it's less likely to travel to another container than it is to stay within the container. So this is the effective distance as we model. It is somehow more discrete than it is in the gravity model, where there's just simply like a function of so the probability of traveling at a given distance is simply like a function of the distance. But here is as if there was a discretization of this dependency between distance and probability of traveling. And precisely because we have these containers.
Okay, so if we need to go through several containers, then we can use a nested logical model. And in particular, we use likelihood estimation, maximization, right? To kind of estimate the number of levels.
Yes, so in a sense, there is a parallel between the container model and the nested logic model. So yeah, that's very much
okay.
That one can think of the container model as a nested logic model for sure.
Okay, so any more questions from the audience? Okay, no more questions. Okay, Jacob, please.
Yeah, I just thinking about that, you know, there's a lot of other models. I mean, I'm not sure how much you go through it in your actual worker paper, but there's just a lot of like models, like from Robert Park, kind of representation of Chicago, that's showing that there's these like rings, or even Beijing, we just alluded to, has the rings. And so I'm wondering if there's, you know, it'd be interesting to see to what extent the containers that you find from your models just overlap with those sort of boundaries that have been either administratively imposed or kind of discovered by sociologists or urbanologists.
Yeah, absolutely. It would be very interesting to compare to other methods. So one of the differences between our approach and other approaches I've seen in the literature is that here is very individual, right? So often we assume that we have like a shared notion of space and structure and spatial structures, but here what we observe again is that everything is very much individual, and everyone has really like their own sort of like hierarchical and spatial structures, and that they don't necessarily overlap even across individuals. So this is why I think this is why our method captures something different than what it's captured by methods that aim at finding like shared definitions of clusters across people, and administrative levels are also one of those. Okay, yeah, I think we come to an end of this webinar. So thank you very much for the very interesting, also the thought-provoking
presentation. I enjoyed very much, and we hope to interact more with you in person in future when COVID-19 is over. So thank you very much.
Thank you
Have a
very
nice
much
day.
for the invitation. It was a pleasure to be here, and also for the nice discussion. Yeah, thank you so
Me
much. It
too.
was very
Me
nice.
too. Yeah, you're welcome.
See you soon.
Bye.
Bye bye.
Have a nice day.
Thank
You too.